welcome back to the IC Engines short lecture series. So today we're going to talk about cylinder geometry, and continuing on from 4 and 2 strokes, we're actually going to look at what a cylinder looks like and some of the equations that are associated with that cylinder essentially. So to start with, what I'm going to do is I'm going to define all the terms that we see in the diagram on the left. So on the left, you can see that we have a piston. So this would be our piston right here. And this piston moves up and down. Okay, so this whole part is a piston essentially. Okay, and it moves up and down. This is a graphical representation. It's not actually what a piston looks like. If you want to look at a picture of a piston, you can search it, or I can put some images or links to images in the description below. So looking at all the numbers and letters on these this diagram here, the one thing that we're going to look at is all the different terms, okay? And I'm going to write out the terms and define them. So TDC is equivalent to top dead center. And what that means is essentially this is the top point at which the piston will reach when the piston is all the way at the top. Then BDC is bottom dead center. And bottom dead center is the point that the piston will reach at the bottom of our cylinder, essentially. So the piston moves between top dead center and bottom dead center. And the distance between top dead center and bottom dead center is equal to a capital S, which is called the stroke of an engine. And so if you're familiar with engines, you might have heard the stroke as a term that we use to describe an engine or to describe some sort of modification to an engine. Then the next term is B, which is called the bore, okay? And essentially what the bore is just the diameter of your piston or the diameter of your cylinder itself, right? So it gives us the actual diameter of our cylinder from wall to wall, and our cylinder is a round. So if you look at from the top view, if you have your cylinder as a perfect circle, the bore would be the distance between these 2 points, okay? Other terms that we can describe, we're going to look at the top of the diagram for now. We'll revisit the bottom of the diagram with the lowercase s, the r, the a, and the theta. The upper part of the diagram, we also have VC and VD. Now, VC is actually this volume right here, okay? And it's called the clearance volume. I'll write it in red so we know that we can associate it with the image, but it's called the clearance volume. And what this clearance volume is essentially when the piston is all the way at top dead center, that is a leftover volume. That is the volume that's left over for the combustion to take place and for the air to be in there. You can't have the piston go all the way to a volume of 0, because if not, you would go to infinite pressure, and that doesn't work, right? Then the other term is VD, which is the displacement volume. Okay, so VD is the displacement volume. And what the displacement volume is essentially the volume from top dead center to bottom dead center. The stroke is the distance, the VD is the actual volume that we come up with. And we're going to come up with an equation for VD in terms of bore and stroke, since we have bore and stroke already. Okay. Some of the other equations that we want to put in place, we see that the piston is directly connected by a connecting rod. So if we look at this piston right here, we have a joint here, and this item right here in red is called the connecting rod. Obviously, it's depicted as a line, but this would be a connecting rod, and it's connected to the crank at the bottom, which rotates in a circular manner. Okay, so this rotates like this. And what we have here is we can say that the connecting rod length is lowercase r. So we can say that lowercase r is the connecting rod length. We can also say that lowercase a is our radius of our crank. Okay, so the crank is what gets powered by the engine, and the crank uses a shaft to transmit the power to a gearbox. Okay, so if we want to look at it in in geometry terms, we can say that S, or capital S, is equal to 2A. Okay, if we look at geometrically, if we see that the stroke is the distance from top dead center to bottom dead center, so we have it right here, the distance from top dead center to bottom dead center, then our A is going to be at top dead center, our point is going to be here for our connecting rod, and at bottom dead center, our point is going to be here. So 2A is essentially equal to this S value right here. Okay, the other equation that we can write is that the average piston speed can be found geometrically from these terms as well. Okay, and everything can pretty much be found from all the geometry here. It's just a triangle and a circle, so it's very easy to come up with a lot of different equations to describe what is happening. But the average piston speed is usually depicted as UP with a bar on top. So typically the bar on top shows that we're looking at an average. If we want to describe it a little bit more, we can say UP average like this. And essentially it gives us our velocity of piston. We don't use V for velocity, we use U just so we don't confuse it with volume. And that UP average is equal to 2 times S times capital N, where capital N is the revolutions per second, or RPS, of our crank. So if our crank is moving at 2000 RPS or 18 RPS or 50 RPS, then we can use that to find the piston speed average. So we're just converting the speed from a rotational motion to a linear motion. We know that S is the distance that the piston covers. So if we multiply S by the revolutions per second, we get a velocity in meters per second, or whatever units we decide to choose. Okay, so that's really important. Now, typically, this is really important. I'm going to write some terms that give us an idea of what speeds we're expecting. Okay, so typically the average piston speed is from 5 to 15 meters per second for most engines. Now, this varies a lot and can be very different, or a little bit higher or lower depending on the application, but typically you would find piston speeds or average piston speeds of 5 to 15 meters per second. That is pretty fast when we think about it, okay? You can convert that to miles per hour or whatever you want, but it's pretty fast when you think that the distance covered by the piston is very, very small. Usually 8 to 10 centimeters, so pretty short distance. The question is, why can't we go higher in piston speed? So you've probably noticed that most cars have a maximum RPM of 7,000 RPM or 6,000 RPM or 5,000 RPM. And one of the limitations is the fact that we can't go too high in piston speed. So some of the limitations that we have, and I invite you to pause the video here if you want to try to think about it before I give the answer. One of the limitations that we have is the material strength. As you move material faster and faster up and down really, really fast, and you increase the piston speed, the material strength has to follow the piston speed that gets put through. So if the material is not strong enough, it won't be able to withstand the piston speed, and the forces will be greater. Remember, when a piston is moving, it's not going at constant speed. It's consistently going between bottom dead center and top dead center, as shown here. So as shown here, between bottom dead center and top dead center, it's consistently moving, but every time it hits top dead center or bottom dead center, the speed is 0 because it changes direction. So it actually accelerates to a maximum speed of in the middle, then it slows down again, then it accelerates again, then it slows down. So it keeps accelerating and braking. And by accelerating, you essentially have a force that is associated with that. The faster the piston moves, the more force goes through the material. So you need to have materials that can withstand that. Now, the other limitation is friction. So typically, when you increase your speed, your friction starts to go higher. One thing about engines is that we need to seal the top part of the engine that we can see on the top here compared to the bottom part of the engine. And we need to seal that. And so that means that there's going to be friction at this level right here. So if we can add that we have some rings here that are going to seal the surface of the piston on the left and the right. And those rings are going to be put to more friction. So another limitation that we have here. Okay, so moving on from this, let's talk a little bit about bore and stroke and how they work. Okay, and we'll introduce kind of the bore and stroke, and then we'll go from there and we'll watch another video where we talk about the displacement of the engine and how we can use bore and stroke and how we can understand what are the positives and negatives of changing the bore and stroke. Okay, so this video will just introduce bore and stroke, and then we'll talk about how that relates to displacement. So bore and stroke are two things that are related together in the sense that they form the volume of the chamber. Okay, typically our bore is going to be equal to our stroke or close by. So whenever you start designing an engine, the first thing that you would do is you would start designing an engine with a bore that is equal to the stroke. Typically, our bore over stroke ratio is around 0.8 to 1.2. So that means that we can vary the stroke and bore away from each other, but typically the values are between 0.8 and 1.2, except in very specific applications. So whenever bore is equal to stroke, what we call that type of engine is a square engine. Whenever our bore is greater than stroke, we call that over square. And whenever our bore is smaller than stroke, we call that under square. So it's a way for us to kind of understand what the designers were trying to do by changing the bore and stroke and the relationship between them. Typically, a square engine would be a starting point, but then you can go into different directions to try and get some positives and negatives from it. Now, we'll talk about in the next video about how we can find the displacement from the bore and stroke. And then if we start with a square engine, how changing the bore and the stroke can create some positive and negative impacts. And we'll kind of talk about them as we go. Okay, so in the next video, we'll talk about that in more depth. So I invite you to watch the next video and subscribe to my channel if you want to. Thank you so much.